Have you ever stopped to consider the incredibly complex dance our electrical grid performs, especially when new power sources like modern inverters need to connect?
It really is quite something, a delicate operation.
Absolutely. And today, we're diving into a really crucial challenge: how to prevent those damaging inrush currents when these newer grid-forming or GFM inverters start up.
Right, that initial connection is key.
So our mission really is to explore this innovative adaptive pre-synchronization strategy. It uses something called Virtual-Oscillator-Controlled, VOC, to ensure these connections are safe, seamless, even when the grid itself is, fluctuating.
And we're drawing insights from a great IKEA transactions paper on this. It lays things out quite clearly.
Okay, so let's start there. These GFM inverters, why are they so important now?
Well, they're becoming absolutely vital. They aren't just passive power pushers. They actively regulate voltage and frequency.
Ah, so they're stabilizing the grid.
Exactly.
Yeah.
Which is essential for modern systems, especially with all the renewables coming online. We need that active control.
Okay, they're critical, powerful. But you mentioned a challenge. What's the vulnerability when they first connect?
The big one is their susceptibility to inrush currents. It's a major headache.
Inrush currents. Explain that a bit.
Sure. If the GFM inverter's voltage and phase aren't perfectly matched to the grid the instant it connects, boom, you get this massive sudden surge of current.
Okay, like a mismatch causing a jolt.
Precisely. Think of merging onto a highway way too fast or slow or slightly angled wrong. It causes chaos, potentially damaging the inverter or tripping protections.
Right, I can see that. And how did we try to handle this synchronization traditionally?
Well, the old pre-synchronization methods, they were okay for what we call stiff grids.
Stiff grids, meaning stable.
Yeah, older systems where the voltage and frequency were pretty constant, predictable. Rock solid, you might say.
But that's not today's grid.
Not entirely. Many parts of our modern grids are becoming low inertia. Think less underlying stability, more reactive.
So their voltage and frequency are more fluctuant? Is that the term?
That's it. They bounce around more. And those old strategies, they assume stability that just isn't there anymore.
Ah, so using old methods on a new type of grid is actually dangerous.
It can be, yes. It can lead to those large inrush currents we want to avoid, damage, system trips. It's a real challenge for grid operators.
Okay, so traditional methods are kind of hitting a wall. What's the innovative thinking needed here?
This is where this new adaptive pre-synchronization strategy really shines. It actually enhances the virtual oscillator control, the VOC.
VOC, remind me.
Think of VOC as making the inverter act like a self-tuning musical instrument. It sort of feels the grid's rhythm, the electrical tempo, and adjusts itself to match.
Okay, an internal metronome almost.
Kind of, yeah. And this specific strategy uses something called an Andronov-Hoff oscillator, or AHO, at its core. It's mathematically quite good at finding that synchronization point dynamically.
Dynamically, okay. And I remember reading something fascinating. This approach works without needing a separate phase-locked loop, a PLL. Why is that significant?
That's a really key point. PLLs are common in traditional setups, but they add complexity, another potential failure point.
Right.
This adaptive VOC integrates the synchronization right into the main control. It simplifies the design, makes it inherently faster, more agile in responding to those grid fluctuations.
So it's all built in, streamlined.
Exactly. It achieves what the paper calls dynamic matching. It actively adjusts the inverter's voltage phase, frequency, and amplitude.
All three.
All three, to match the actual time-varying grid conditions. And crucially, it does this before the connection happens.
So it's not aiming for a fixed target, it's tracking a moving one. How does it know what the grid is doing so accurately?
It uses clever internal feedback loops. The paper mentions specific integral components, let's call them PEs and QBs.
Okay.
These components constantly measure the difference and adaptively regulate the inverter's output power before connection, driving the voltage and phase differences to zero. The goal is perfect steady-state alignment. Inverter voltage equals grid voltage, phase angle difference is zero.
Wow, okay. That sounds impressive theoretically, but does it work in practice? The paper had experiments, right?
It did, and the results were really promising. They showed it successfully mitigated those inrush currents.
How successfully?
They achieved what they call seamless addition, a smooth connection, even when the inverter started completely out of phase, like 180 degrees difference.
Whoa, 180 degrees. That's diametrically opposite.
Exactly. And it still managed a smooth merge. It shows how powerful that adaptive listening is before the connection.
That's incredible. It's like it perfectly matches speed and merges lanes without a ripple. What about those tricky road conditions you mentioned? Off-nominal grid states.
That was another crucial test. It adapted remarkably well when the grid frequency wasn't the perfect 60 Hz nominal, for instance, at 59.7 Hz.
Okay, a slight drift. What happens normally?
Well, with traditional methods in that 59.7 Hz scenario, they observed a significant 15-degree phase difference lingering right before connection. That's exactly the kind of thing that causes inrush.
But the adaptive method.
Handled it. It aligned properly despite the off-nominal frequency. It also managed grid voltage deviations, like being 10% higher or lower than expected.
So it's robust.
Very. It leads to safer and smoother connections, which is exactly what you need in these dynamic, sometimes unpredictable power systems.
Right. So wrapping this up, what this really means for you, our listener, is that this kind of smart adaptive control, it's absolutely pivotal.
It's how we safely integrate all these new power technologies into grids that are, frankly, becoming more complex and dynamic every year.
It's about building systems that don't just push power, but actively listen and respond to the grid's rhythm.
Precisely. Ensuring stability, reliability. It's fundamental.
And that final thought, this idea of intelligent adaptation before connection, it makes you wonder, doesn't it?
It really does. How could similar pre-synchronization thinking, that idea of sensing and aligning before acting, how could that revolutionize other complex systems? Oh, maybe robotics. Robots in a shared space perfectly syncing movements before they get close to avoid collisions. Or smart city infrastructure, components seamlessly integrating into a constantly changing urban environment.
Yeah, not just connecting, but connecting smartly based on real-time conditions.
Exactly. It's a really powerful concept, I think, with potential far beyond just the electrical grid, something to definitely think about.